Okay, so propositional logic, the applications of the propositional logic. So there are penalty of the applications. There are variety of the applications. Some are listed here, and few of them we will discuss today in this class. Like for example, translating the English to propositional logic. This is really important because our native language, we speak in human-centered language like English, and when we convert it into the programs or the computer programs, we have to form some logic, right? So we always try to convert the English language into the propositions and apply the propositional logic so that we can use it with we can program it in computers, right? System specifications, Boolean searching, logic puzzles, logic circuits, AI diagnosis methods, and many other applications of the propositional logic are there. But we will see few of them. Be with me and we will be discussing some of them. So as first, translating the English sentences. So this is basically a step. We follow some steps to convert English sentences or to a statement in propositional logic, right? So we want to convert the English sentences to the statements. Remember what is the proposition? Again, let me give you recall it. In the last class, I already told you the proposition is some statement that is either true or false, right? So a statement, if it is true or has a false value, is called a proposition, but it cannot have the both values or like that, right? So what is the process and what are those steps to translate this, to convert this English sentence to the statement? So let's see. So for example, first of all, what you need to do is you need to identify atomic propositions. Identify what are the smallest proposition available in this sentence, right? So identify atomic proposition and represent using the propositional variables, right? So we'll see the example right now and we will understand. And then determine appropriate logical connectives. So for example, if this is the, if I have an English statement, if I go to Harry's or to country, I will not go shopping. So how we can convert this English statement into a propositional logic? See, so there are two steps as we discussed. First of all, identify the atomic proposition. So let's identify. So the one atomic proposition could be I go to Harris, right? Another proposition could be I go to the country, right? Another proposition could be I will go to shopping. Remember, whenever we are writing the English statement, atomic statement into a proposition, we usually ignore the not and other sort of things. So we straightforwardly say this complete sentence. Let me say if P is representing, P is a propositional variable and I assign the value, I go to Harris, right? So this statement will be represented with P, and Q is going to represent I go to the country. That is again the atomic that is again the atomic sentence, right? As they're considered as a proposition. And I have one more variable R, right? That is representing I will go to shopping. I will go shopping, right? So how can I now write this sentence into a proposition? Since I have three variables now, P, Q, and R, and they convey some meaning. P represent that I go to Harris, Q represent I go to the country, R represent I will go shopping. And the sentence is, if I go to Harris or to the country. Now see, this is what, this is my P, this is Q, right? So you can see P representing I go to Harris, Q representing I go to country. And the statement is, if I go to Harris or the country, means I can write it P or Q using the connective, remember from the last class, right? So this P or Q I can write to show this statement. I go to Harris or to country, right? But then there is an if. And we know that what is if then else structure in propositional logic, that is implication. I explained it in the last class. So if I'm using the if then, right? So I am following this implication structure, right? So that means P or Q implies something. What is that? It implies I will not go to shopping. R is representing I will go to shopping, right? So, but in this sentence it is not. So what I am going to do, I am having that implies negation of R. Is that clear? So we converted this sentence into the proposition using the propositional variable. And what are the steps? Let me repeat once again. What are the steps? First of all, you need to identify the atomic propositions. Then you need to see what variables you are going to use for those atomic propositions. Assign those atomic proposition to the variables, right? Then you have to see the structure of the sentence and use the connectives and the very different connectives, logical connectives of the propositional logic in order to form the proposition. Now this proposition is conveying the same meaning as this sentence. Is that clear?
Yes.
Right? So that's how we are going to convert the English sentences into the proposition. Let's have one more example. Let's have one more example. So to translate the following sentence in propositional logic. So you can do it by yourself. Take a paper and pen and solve it with me, right? You must have a paper and pen with you so that we can solve different questions. So take a pen and identify the atomic proposition. So the sentence is, English sentence is, you can access the internet from campus only if you are a computer science major or you are not a freshman, right? So let's identify the propositions, right? So atomic proposition number one is you can access the internet from the campus. This could be one proposition. Let me represent it with A, B, C, whatever variable you are willing to do. Let me represent it with A, right? So just give me 1 minute. Let me erase this. Okay, so let's represent it with A, right? Then another atomic proposition could be you are a computer science major, right? Let me call it B, for example, and then you are a freshman. I am ignoring this not. I already told you we do not consider this not because it is a negation operator, and when we are going to assign it to the propositional variable, we ignore this not sort of thing. So let me call this A, right? So this is what we have identified the atomic proposition, and we have assigned the variables to those propositions. Now you can see what is this. Let me just recall this. You are a computer science major or you are not a freshman. What does this mean? You can use it that if only these are the conditions, then you can use the internet. What does it mean? It means if you are B, right? If you are a computer science major or not a freshman, that means not C, right? Only then you can use the internet. You can access the internet. It means that implies you can now use the internet, right? So this is what the proposition, the equivalent proposition of this English sentence. Got it?
Yep.
Right? So this is how you can translate different sentences, English sentences into the propositional logic, right? Okay, let me give you one sentence and can you convert it for me in the propositional logic, right? Let's say, for example, if it is not raining and it is Friday, I will go to campus. Let me recall it again, repeat it. If it is not raining, and it is Friday, only then I will go to campus. Yes, take 2 minutes and convert this English statement into the propositional logic. I'm waiting for you guys.
Okay.
Yes, anyone has solved it?
It's negation of P and Q, and it implies R.
Excellent, excellent. You guys did it right. So if it is not raining means not P, right? And it is Friday. That means and it is Friday means Q. Only then I will go to the campus employees are. Excellent, right? So I'm sure now you got the concept that how we are going to convert the English statements into the propositions. Clear? Let's move next. Okay. System specifications. So being the computer science guys, we know that we have to develop systems that involves the hardware and that also involves the software, right? So software systems and the hardware system. So what does the system analyst do? System analyst go and check your requirements, takes the requirement specification, and based on those requirement specification, they design the computing system for your organization that may be based on the software and the hardware. So system and software engineer take requirements in English and express them in a precise specification language based on the logic. One of the obvious reason is that English if we write in English, that may be the ambiguity. There may be the ambiguity if we write it in English. There may be the ambiguity for programmer, for analyst, for other personals as well. So we always convert it into the logic so that programmer can easily understand that, right? So for example, if we have the statement like this, express in propositional logic, the automated reply cannot be sent when the file system is full. Yes. This is again the English statement. Can we convert it into the propositional logic? Please take 2 minutes and convert it into the propositional logic. Yes. Okay, we don't have much time. Here is the one solution. There may be the many solutions, but one solution is let P denote this P is we assign some value to the P. The automated reply can be sent. The first atomic statement, the automated reply can be sent. You are not doing the not. You are going to ignore it, as I earlier told you, right? And Q denotes the file system is full. So it's obvious. I mean, the reply, automated reply will only be sent when the file system is not full, right? So that means this Q implies not P, right? For example, if Q implies not P means if the file system is full, reply will not be sent. This is one solution. There may be the another solution. What is that? What is that? Not P implies not Q. The message will not be sent if the file system is full. Oh, sorry, this is not Q, right? It's not P implies Q. So in both ways, this is working. Okay, one of the important concept is that system specification should be consistent, right? What do we mean by the consistency? Let's have a look over the definition. So a list of proposition is consistent. We have list of propositions, various list of propositions, right? And we want to check the consistency. It is consistent if it is possible to assign truth values to the proposition variables so that each proposition is true. So if, for example, if I have these three proposition statement values, right? Three propositions, and if I assign the value to these proposition and then I can get the answer as a true, so then these three statements are consistent. These three propositions are consistent. If I get not the true value for all of three, the specifications are not consistent. Let's have a look. Let's convert them into the propositional logic and then let's see. So these statements are: the diagnostic message is stored in the buffer or it is retransmitted. This is number one. Number two is diagnostic message is not stored in the buffer. Third statement is, third proposition is, if it is if the diagnostic message is stored in the buffer, then it is retransmitted. So let's see how we can convert it into using the propositional variables and then see whether if they are consistent or not. So let's look at solution. So let's define, let P denotes the first one, right? Let the atomic proposition. What is that? The diagnostic message is stored in the buffer, right? So P is denoting this. What is that? The diagnostic message is stored in the buffer. And Q denotes, Q says the diagnostic message is retransmitted, right? So, and then let's see what the first statement says. First statement says the diagnostic message is stored in the buffer or it is transmitted, right? If this is P and this is Q, we can represent it using the P or Q, isn't it? So P says the diagnostic message is stored in the buffer or it is retransmitted, right? So it is retransmitted is Q. So P or Q can represent this first statement. Number one, let me write it over here, right? Okay, the second statement is that diagnostic message is not stored in the buffer. That is simple. P, the negation of P, right? So that's the negation of P. And the third statement is, if the diagnostic message is stored in the buffer, then it is retransmitted. What does that mean? It's simple. P implies Q. So this is statement number 2. This is 3, right? This is how they are represented using the propositional logic. Agree, right? Now see, we have just converted those these statements into the propositions with the help of the propositional variable. Now see, when P is false and Q is true, all three statements are true. So we have the statements, let me write it over here. P or Q for the number 1, right? We have the not P for the number 2. P implies Q for the number 3, right? So what do we mean by the consistent system specification? As I earlier told you, so you put some value and for each proposition it should be true, right? You get the result true. So when P is false, so for example, the diagnostic message is not stored, right? Then we can see all the proposition will result true. So for example, if this P is false and Q is true, so we get the result true. So we are getting result for true for P and P or Q. If P is false, and negation of P will result in true, right? And if P is false, Q is true. So we already know the truth table of the implication. False implies true will always result in true, right? So all of these three statements are consistent if the value of the P is false. So then what we say, when P is false and Q is true, all three statements are true. So the specification is consistent. If any one of them becomes false, the specification is not consistent. Is that clear? Right?
Yep.
Okay. So, okay, next. Okay, what if the diagnostic message is not transmitted is added? The number 4, statement number 4 is diagnostic message is not retransmitted, right? So what does it mean? That means we are actually adding the negation of Q. Why? Because Q represent the diagnostic message is retransmitted. So if we have the uh, fourth statement, that is the transmission is the diagnostic message not transmitted. That means negation of Q, right? So if we have negation of Q where we are putting the Q as the true value, so this will become false, right? So that means this statement is not consistent with all these three, right? So that's what it says. So the specification is not consistent. If any one of become false, the specification is not consistent. Okay, next. Oh, let's solve the puzzle. How many of you like the puzzles?
I don't.
Oh, come on.
Me neither.
Okay, okay, no problem. But puzzles usually they boost your logic, they enhance your logic. Let's see. Let's have one puzzle, and obviously we all together will solve it. So don't worry. So it says the puzzle posed by the Raymond Samuels. It says that an island has two kind of inhabitants. One are knights who always tell the truth. The property of knight is they speak truth, and knaves who always lie. So two type of people are living in the island. One are knights, another are knaves. So knight always speak truth, knave always speak lie. So you go to that island and you met two people, A and B, right? A says B is a knight, right? And B says the two of us are of opposite types. So now tell, what are the types of A and B? Are they knave, are they knight, or both are knave, or both are knight? Okay. So how do you say that both are knaves? Can you please explain?
Wait.
Yeah.
Is P is the basis to
I mean, I got one message that who's this Borme. Borme says that both are naive. Can you please explain why and how?
both are A.
Well, let's see
Wait,
the solution of the problem. It means, look, we have two scenarios. A says B is a knight. What does mean? It means if B is really a knight, then B is not telling the lie, right? If A is a knave, then this should be the lie, right? So let's see, let's solve this puzzle. Let P and Q be the statement. Let's denote these statements with two propositional variable P and Q. So that A is a knight is represented with P. I mean, this is P, and B is a knight. This is Q, right? So then, not P will obviously represent the proposition that A is a knave, means A is not a knight, right? A is a knave, and not Q will be representing that B is a knave, right? Okay. So let's think about it. If A is a knight, right? If A, for sure we have to assume if A is a knight, then P is true. Why? Because A never speak lie. Because if it is a knight, it will always speak true. So it means P is true. P is true means A himself is a knight, right? Since knights tell the truth, Q must also be true then. Why? Because A is saying B is also a knight, right? So so we can simply write it like this: P and not Q, right? Or not P and Q. One of them is the true, right? The answer should be true. Listen again. If A is a knight, then P is true, right? Since knights tell the truth, Q must also be true. Why? Because this statement B is a knight is said by A. That's why it should also be true. So if this is the scenario, so P and not Q means P is true, P, A is knight, and B is a knave, or A is a knave and B is a knight. This one of them must be true. I mean, the answer, the total answer would have to be true, right? But it is not the case. So A is not a knight, and therefore not P must be true. See why? So okay. So the statement here is P and not Q, or not P and Q. Let's assign them the values. It says if P is true, means this is true, so then B should also be true. That means this is false because of the negation, right? Or if this is not true, I mean P is not true, A is not a knight, then this is false and Q is true, right? So this is false. If you get the answer true or false is false, or false and true is also false. So total will result in false. So it means this is not the case, right? Okay. So if A is a, I mean that means if A is not the knight in this case, this statement is false. We have mathematically proven that using the logic propositions. Okay. If A, the second case, if A is a knave, that means it is speaking a lie. It is telling a lie. So then B must not be knight, since knave always lie, right? So then both not P and not Q hold, since both are the knaves. So both are the knaves. Why? Because if if A is a knave, so he is speaking lie, that B is a knave, and if B is the knave, then this statement is false, because they always speak lie. It means both are the knaves, right? Yes, you are right, but we have to prove it mathematically. Is that fine?
yep.
Okay. Okay, next, logic circuit. This is really important, and we will discuss this in detail in coming chapters, right? In chapter number 12, especially with the Boolean algebra. We'll be discussing it later on, maybe after 7-8 weeks, right? So we know that the digital computers or the digital devices, they are made up of circuits, right? And these circuits are implementing the logic. Softwares are the soft logic that we are implementing using the softwares, but the circuits, they are embedded with the softwares. They do follow the logic as well, right? So we embed the logic there. So normally what happens, we have true values now, two values, one is true or false or true. So usually if we represent it using the binary, I already told you 0 represent the false value, 1 represent the true value. So this is universal for the computer science. Everywhere, whenever you find 0, it means we are talking about false, or whenever we are talking about false, it means we are saying that the 0 binary value, and true represent 1, right? So what are the logic circuit? We already know that we have three type of operation, basic operation, that one is the negation, another one is the OR, another one is the AND, right? So we have three logic gates for them. So this is the inverter that inverts the input into the opposite. What if P is true, the answer would be false. If P is false, answer would be true. So this circuit logic gate that we call inverter inverts the whatever we input it as a output, we will get the inverted output, right? This is the logic symbol or logic gate for the OR gate. So it have two inputs, one is P, another is Q, and it gives the OR of those two values. That means if P is true, Q is true, what will be the answer? Obviously true, right? Any one of them will be true, either P or Q will be true, we will get the true value here as an output. Clear? This represents the AND gate, right? So AND gate, there is a slight difference between the symbol. So this is AND, this is OR. Remember this. We'll be using this later in this course as well. So this is also two inputs, P and Q inputs, and it gives the output of the R, right? P and R. It gives the output of AND, P and Q, right? So if any one of them is false, the answer will be false. We already know the truth table of AND. So in order to get true here as an output, these both must be true. Otherwise, the answer is false, right? So we have the circuits available in the market. The ICs are available that implement those logic gates, right? And with the help of these basic three logic gates, we can have a complex circuit like this. So for example, if I have the Boolean expression P and not Q or not R, right? P, that is written over here, P and not Q or come on. Anyways, let me write it again. P and not Q or negative R, right? Negative R. So we can implement it with the help of one AND gate, two negation gates, negative gates, and one OR gate. So that's what we have. We have P, Q, and R. We are giving P and not Q as a one input. So we have one AND gate, right, where we get P and so P directly, but we need not Q, right? So we have one inverter first, then the result of that inverter is negative not Q, that is going to be input with the AND. So as a result, we will get P and not Q, and then this has to be ORed with negative R. So there is the OR operator. The result of this P and not Q will be the first input, R with the inverter. The negation of the R will be the another input to the OR gate, and we will get this result here, right? We can represent using the truth table as well. So you can write, your task is to convert this circuit into the truth table. So mark it for your homework as well. So what you will do, you will actually create the truth table for this P, Q, and R, this logic circuit, right? Okay, any questions so far before moving to the next section? No question?
Yep, no questions.
Okay. Let's move next then. Propositional equivalences. So what does this mean and what actually it is? Let's discuss about this one. So we'll be talking about the tautologies, contradictions and contingencies in this section, and we will also be looking for the logical equivalence of two propositions. So what do we mean by the tautology or contradiction or contingency? So understand this. This is again one of the important concept. So a tautology is a proposition which is always true. So if there is a proposition and you get the result always true, so it can never be false, then such type of proposition is called tautology. One of the classical example here is P or not P, right? If P is true, for example, if P is true and not P is definitely is the false, if you take the OR of this, you will get the true answer, isn't it? If, for example, P is false, then not of P will always be true, right? So the negation operator will convert it. If you take false or true, you will always get a true result. So tautology is whenever you get the true result for that proposition, every time that proposition is called a tautology. So you can never make it negative, false. Is that clear? Next. Contradiction. Contradiction is opposite of the tautology, is a proposition which is always false, right? So you always get the false results, then the result can never be true in this case. So that's what so then we call it a contradiction, right? For example, P and not P, one of the classical example. If P is true, right, not P will surely be false, right? And if you take the AND of true and false, this is always false, right? If you remember the truth table of the AND table from the previous class. And if P is false, right? So not P will always be true, right? So if you take the AND of false and true, this will result in false. So such type of the propositions are called contradiction, right? Is that clear? Are you getting me?
Yep.
Is my voice clear?
Yes, yes.
Okay. So the third concept is the contingency. Contingency is a proposition which is neither a tautology nor a contradiction. It means sometimes it is true, sometimes it is false. If sometimes it is true, sometimes it is false, we call it a contingency, not a contradiction, not a tautology. So let me just summarize it. Tautology is a proposition which result always true. Contradiction is a proposition whose result is always false. Contingency is neither true nor neither a tautology nor a contradiction. Sometimes it is true, sometimes it is false. Logical equivalence. Okay, so the compound propositions P and Q are logically equivalent, right? So we basically, if you remember last time we discussed this one, bidirection. P bidirection Q. This is an after implication we discussed this bidirectional propositions, right? So what we say, two compound proposition P and Q are logically equivalent if the bidirection of P and Q is a tautology. Means it's always give you the true result, right? So we'll prove it and we'll discuss more about it. So we write it as P, a bold arrow with Q, or we call it P, three dash signs, that is, not the equal, but the three signs for the equality, P equivalent to Q, where P and Q are the compound propositions. So two compound proposition P and Q are equivalent if and only if the columns in truth table give their true values agree. So obviously this is the way to prove, always to construct a truth table and then find the truth values. Let's see. So the truth table for the negative P or Q is equivalent to the P implies Q. It says prove that these two statements, it says these two state propositions not P or Q and P implies Q are the logically equivalent. Let's see. So the best way is to have the truth table, and that is already here. So we have two propositions P and Q. So these are the possible combinations: true, 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 false, false, true, and false, false. So we have to find this not P or Q first of all. Then we will have the not P here. So not P is, if it is true, it is false, true, false, false, then it is true, it is false, then it is true. So this is the column of not P, right? Then we have to find it not P or Q. So not P or Q. So let's see. So not P false true, or there is an or operator, any one of true, it is true, right? False true, it is true. False false, it is false. True true, it is true. True false, it is true, right? So this is the result of not P or Q. Now let's find the P implies Q. If you remember the truth table of the P implies Q, it is only true, only false when P is false. Sorry, it is only false when P is true and Q is false. Otherwise, it is true. So that's why true true it results true. True false it's false. False true it is true. False false it is false. So this is the truth values of P implies Q. And if you see, these two values are same, right? So true false true 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 false true true. So that means when they are giving the same result on the same proposition, so this is logically equivalent. What does it mean? It means not P or Q is logically equivalent to P implies Q, right? Is that clear?
Yep.
Okay. So next, one of the favorite, De Morgan's law, right? So we already know the De Morgan. The De Morgan's law says that if you have the proposition like this, that is P or and Q and the negation to the whole, P and Q and the negation as a whole in the bracket. You can always divide the negation. I mean, like this. You can have the negation with P. You can have the negation with Q. But then this and symbol will be converted into or, right? So if you have not P and Q, so De Morgan says you can this is logically equivalent to not P or not Q. We have to prove it. We will prove it using the truth table, right? The second law is if you have not P or Q, so you can do the same. You can convert distribute this not with the P, you can distribute this not with Q, but then this or sign will be converted into and, right? Just opposite side. So let's prove this using this truth table. So we have two propositions P and Q. So these are the possible combinations: true, 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 false, false, true, and false, false, right? So we need to prove that De Morgan's law. So we have to negate. I'm getting the negative P here, right? Whatever is the value of the P, negative of those. If it is true, true, false, false, it is false, false, true, true, right? So negative Q. So true, false, true, false. This is false, true, false, true. I'm reading it in the sequence, right? So now P or Q. P or Q, we already know the truth table. Any one of true is true. So P or Q. So here true, true, it's true. Here it's true, false, it's true. False, true, one of them is true, true. False, false, both are false. So this or operator is false. So this is the value of P or Q. Now, not P or Q, right? Not P or Q. So what does it mean? This negation is outside with the P or Q, means you have to apply the negation here in this column, right? So if this is true, 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 false, so this will become false, 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 true, right? and at the end we are going to take we are going to distribute this negation inside, right? Not P, not Q with the AND operator, not P and not Q. So we already have not P, we already have not Q, so just AND these two. So false false will end false, false true will end false, for true false will end false, true true will end true, right? So true and true is true only. So now if you see these two results are same, right? So these two results are same, so that's why I can say negation of P or Q is logically equivalent to not P and not Q, right? We have proved it using the truth table. So this is about this one, right? Can you add one more column in order to prove this? Hurry up. Take 2 minutes and solve this. Solve this. So first of all, you need to find the P and Q, like we found here the P and P or Q. So you will find P and Q and then apply the negation and then find this one. And these two results must be same. Yes.
Yep, it's right.
So you already proved it. How about others?
Yep.
Other students, please open up your mics and let me know, have you proved it?
Professor, I am working on it. Wait.
Sorry?
Please wait. I am solving it.
Okay. Okay. Oh, we do not have much time. You can do it later. I mean, but you have to prove it. You can start, keep working. Yeah,
Professor, okay, I see it. I solve it.
you solved it. So all
Yeah.
other class members, I mean, they have to solve it later, but do it as I mean, we don't have much time right now because we have to complete this lecture and we are running out of time. Anyways. So there are some laws for equivalence, right? Okay, so one of the law is that we call the identity law. Identity law says if you and any proposition with true value, right? Any proposition with true value, doesn't matter the result of this is and or this is this is true or false. This is always result logically equivalent to the P. So just prove it in one shot. Let's say, for example, if this P is true, this will always be true, right? Isn't it the same result of the P? If P is false, P and true will result in false. Again, this is the P, right? So identity law says if you AND any proposition with true value, you will get the result, same result as the proposition. But if you if you OR it with any proposition with false, you will get the same value, right? So this is the identity law. You can prove it again. And if P is true, you are going to do it with ORing it with false. You are getting true value here. That's again same as P. If P is false and you are going to OR it with false, the result is false, right? That is again same value as the P value. So this is the identity law. Domination law. Domination law says if you OR any proposition with true value, this will always result in true, and that's true. For example, if P is false, right, and if you OR it with true, even you are getting the true value. If P is true and you are ORing it with true, again you will get the true value. So the domination law says whenever you OR any proposition with true, you will get true as a result. And the second law of domination says if you AND any proposition with false value, you will get the false value. Again, this is true. I mean, for example, if this P is true, if you AND it with false, you will get the false. If P is false, even you AND it with false, you will get the false result. So you need to remember and prove these laws for future use. Idempotent law. Idempotent law says if you take OR of the same two propositions, that is again you will get the same result, right? If you AND two same proposition, you will get the same result. You can prove it for any value. If you are going to P is true, then definitely you are going to P is true for the both sides. So true and true will result true, that is again P. If P is false, you are going to AND it with the P, that is again false, you are going to get the false result, that is again P, right? So double negation law. Double negation law says if you have a negation and negation of P, so negation and negation will cancel out, it will result in P, right? Okay, the negation law. Negation law says if you OR any proposition with its negative or its negative, so you will get the true result. For example, if you are ORing P with the not P, you will get the true result, and that's quite obvious. If P is true, not P will be false, and when you take the true OR, this will always result in true. And the second negation law says if you take AND of two same propositions, P and negation of P, you will always get the false result, and that is again true. If P is true, not of P will definitely be false, and if you take the AND, then this will be the false. That's the negation law. Commutative law. Commutative law says if you have P or Q, this is equivalent to Q or P, no matters. No, the order does not matter here. If you take P or Q, you take Q or P, they are equivalent. Similarly, if you take P and Q and P, they are same. They will result the same, right? So they are equivalent. So the commutative law. Associative law. Associative law says if you have something like this, P and Q, bracket says, remember in the last class I also explained the precedence of the operators. So in this case, first of all, you will solve this bracket P and Q. Whatever is the result, that will be ended with R. All right. So the associative law says if you do this or this, the result will be same. Means if you take the Q and R first and then take it with P, so it doesn't matter, they are logically equivalent. Same is the case with the OR. If you take P or Q or R, P or Q first, then OR with R, so it is same if you take Q or R first and then take the or result and take it with or with P, right? So they are logically equivalent, and this law is called associative law. Distributive law. Distributive law is if you have something like this, P or Q and R in the bracket, P or Q and R. So you can distribute this P with Q and P with R as well. Like what? P or Q separately, right? P or Q separately, and then P or R separately, and then this and will be in between, right? So that's the distributive law. Same goes with the and as well. If it is P and Q or R, so you can distribute this P and Q, and then P and R, right, separately, and then R in the middle for the results. So they are same. That's called the distributive law. Absorption law. Absorption law is if you have the proposition like P or P and Q, right? P or P and Q, the result is P. You can prove it. Like if you have P is true, right? And Q is also true. So P is true and Q is also true. This will result in true. So the result will, this is true. And when you take the OR with P, the result, the result will be true. That is equivalent to P. If P is false, right? P is false, even Q is true, for example, this will result in false. False and true will result in false, and then when you take false or false, this will result in false, that is again P. So that is the absorption law. If you have P or P and Q, this will result in P. Similarly, if you have P and P or Q, this will also result in P. All right. So they both are equivalent. So that's the absorption law. Okay. So there are some more logical equivalences are there. So for example, this one P implies Q is equivalent to this one. I mean, we have already discussed many of them, but you can do that. What is your task? What you have to do is mark it as your homework. What you need to do is you need to prove these equivalences with truth table. What does it mean? You have to create the truth table for all these statements, and you have to prove that. Okay, so just for example, this one. Just for example, this one. You have to create a truth table in order to show that this is illogically equivalent to this one. This is proven already, but you need to prove it using the truth table. Is that all clear? Okay, so we can construct the new logical equivalences as well. We can show that two expressions are logically equivalent by developing a series of logical equivalence statements. If you remember all these equivalences, these laws, we can solve this very easily, very in a very equivalent manner. Let's see this this proposition as well, right? One of the proposition. So you can prove it using a truth table, or you can there are two ways to prove it, right? To prove the equivalence, there are two ways to prove it. One is the truth table that I ask you to prove it. Another way is the using the laws, using laws. What laws? These laws, equivalence laws. Okay, identity law, dominant law, these are laws. If you remember these laws, you can always convert it using the laws, right? Some of the examples are here using the law, but using the truth table, you can do that. You have to do it as your homework. So for example, if this is the statement, negation of P or negation of P and Q is logically equivalent to negation of P and negation of Q. How we are going to prove that? So for sure we will use this one, and we will reduce this to this one. How? So we know that if this is negative P and a negative negation of, okay, this is the negation here. By using the De Morgan's law, second law, we can have this negation inside, right? So what we did, we multiplied this negation with this one and this negation with this whole, right? So when we do this, this will become negative negation of P. This will become negation will be here, and inside will be there. But this OR symbol will be opposite, converted into the AND symbol. So that's how we use the De Morgan's law of negation to distribute the negation. So negative P, negation of P and negation of this whole, that is negation of P and Q, right? Yeah. So now what next? We know that, okay, so now this is the negation outside. Let's apply it here. If you remember the precedence law from the previous lecture, I told you after the brackets, the highest precedence is of the negation operator, right? So now solve this negation. So if we distribute this negation inside, so this will become negation of P. This sign and sign will be converted into or sign, and this negation will also be with negation of Q. So this is how, with the help of the second law, again the first law of the De Morgan's law, first De Morgan's law. So negation of P or negation of Q. Now this becomes the double negation, right? Double negation. We know that double negation will be cancelled out. So negation of P is there and is there. So this negation and negation is cancelled out. That is P or negation of Q. So this is reduced to this one. Now we know the distributive law. We can distribute this negation of P inside, right? So negation of P with this, negation of P and P with this one, negation of P and negation of Q, right? And or will be in between. So that's how we have formed this this proposition. So negation of P and P or negation of P and negation of Q, right? So we already know from the previous laws that negation of P and P is actually equivalent to false, right? Remember from the previous year, right? That is always false. Negation of P and false is always false. So we already have proven it. So this whole will become false, or negation of P and negation of Q will remain there. So if you if we rearrange it, I don't feel any need to rearrange it, but yes, let's rearrange it. If we take this first and or with false, so we know that anything, if we take the any of the thing, if we take or with false, the answer will be the same, this one, right? So again we have proven it here. Anything if you take or with false, if you take or with false, it will remain false. If you take okay, so where is that? But anyways, you will find it here. I cannot see right now, but the solution is, whenever you take the or with false, this false has doesn't this based on the identity law, right? So this is reduced to this one. Just 1 minute. I don't know why it is messy today. Okay, let me take the pen again. So if this is reduced to this one, and that is equivalent to this, right? So this and this are logically equivalent. This is how we prove it with the help of the laws. You can do the same with the help of the truth tables, and you have to do that as your homework, right? So one more example before moving forward. P and Q implies P or Q. So let's see, it's a tautology. Prove that this is a tautology. Tautology means this will always result in true. At the end, we will get true. I mean, this whole is logically equivalent to true, right? So let's see if we can prove it. So P and Q implies P or Q. So with we know the truth table of this negation. This is logically equivalent to, from the previous slides, we have seen that this is not P and Q or P or Q. They are equivalent. If you remember from here, we have just proved it here, right? Like here, right? So basically we proved here not P or Q is equivalent to P implies Q. If P implies Q, this is equivalent to not P or Q. Means convert this P with the negation, and we can take Q as it is with the or operator. So same we did here, right? So if I consider this whole as a P, this whole as a Q, so this whole will get the negation. This symbol will convert it into the or operator. This will remain the same. All right, and then we can see this divergence law. First divergence law for this negation. This negation will be with P. This symbol will be converted to OR, and this negation will also be with Q as well. So not P or not Q, and this remains the same, or P or Q, right? So based on the associative law and the commutative law, we can rearrange it. So not P or P, not Q, we can just, since these all are the or we can rearrange it based on the associative and the commutative law. So we rearranged it in a form not P or P, not Q or Q, Q and whole Q. So this will always result in true. This will always result in true. We have already seen the truth table, the laws earlier in this lecture. So true or true will always result in true. If it always results in true, that means it is logically equivalent to the true. That means this proposition is a tautology. Right. Next. That's all for today lecture. If you have any questions or comments, you can ask or you can say anything you want.
Okay, Professor. So the homework for today, it's only for drawing the truth table for each of those.
Well, it's not only this. I will post it on the canvas. You are still, remaining with the previous homework. Basically, first of all, you have to convert this truth. You have to prove all these with the help of the truth table. Number one. Number two, solve the exercise 1.1 that I given you in the last class. And today we have covered two sections, 1.2 and 1.3. So two more exercises are there. So if you solve the exercises, that will be, your understanding will be clear and you will not be in trouble during the exam. So yeah, but you can do it and you can submit it by the end of next week, no problem. But for the previous homework, you have to submit it by the end of this week.
Okay, but it's just kind of a lot because we have other stuff to do too, and
I can understand, but
like the last homework is 4 A4 pages and it's still not done.
okay, I will post the selected questions. Is that fine?
Yeah, if selected questions would be better because if we have to do all of it, it's kind of a lot for us.
No problem. I will post the selected questions.
Okay, thank you, Professor.
Welcome. What else?
Yeah, that's all. I just wanted to say it's a lot.
Okay, no problem. I can understand that this is voice from the whole class. Okay. I have to make one announcement. Well, I was thinking to not having regular Zoom classes. What do I mean is, if I record my video lectures and I put it and share the video lecture with you guys, you can watch the video lecture, then prepare all the questions, and then we can have one session in week for maybe 1 hour or 1.5 hours maybe to just answer those questions rather than teaching like this. I am thinking to record the video lecture so that if someone of you are not able to even join or miss the class, so the video, you can watch the video lecture and then we can have one day in a week to answer the questions only. Is that fine?
That would work for me.
I think that would work for everyone because
Yeah.
it's the interest of everyone. You will get the recorded lectures and you can watch it anytime based on your convenience. Whenever you get time, you watch those lectures. But make sure before coming to the class, we will be having one class only in a week. But before coming to the class, you watch those lectures.
Yep. Okay.
So I think it's fine. So next week we have class on Tuesday. So before Tuesday, I will upload the lecture and we will not having the class on Tuesday. So basically we will upload 2 lectures in the coming week before Thursday. So that you can watch those lectures, and on Thursday, the same time, we will be having a class just to answer your questions if something is not clear in the video.
Okay.
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 That's great. So anything else or any comment if you want to say? Are you getting? I mean, is it fine? My teaching way is fine. Uh, you are understanding what I am going to convey or teach. Is that all fine, or should I need to change a bit so that you guys are comfortable?
Yeah, the teaching is fine. It's just that the homework is a lot.
I
That's
think
all.
that's the solution. I will post the selected question. Don't worry.
Yep. Okay. Thank you. That's it.
Okay, then take care and have a very good day. I will mark the attendance.
Professor, I have one more question.
Yes, please.
Yes, I have a question regarding with the homework again. Are you require us to write on the paper or we can type it on our computer? Because I find it easier to type on my computer if the homework is that amount.
I don't mind typing or writing on the paper until or unless it is not copied. Right.
Okay.
So I mean, it's not allowed that you just copy from the internet or from your friends. That is not allowed, and definitely I have the plagiarism softwares that will detect it. You have copied or you have done by yourself. So that is not allowed. But otherwise, I don't mind if you can type or if you can write or if you can use a paper and pen. I don't mind. Whatever you feel easy and comfortable would work for me.
Yes. Yes. Thank you, Professor. Thank you.
Welcome. Welcome. Okay, so for the attendance, I will mark attendance based on, because I have the recording, I know the names here in the list. So I will mark the attendance based on your names present in the class. So have a very good day, take care, and bye-bye.
Bye bye.
Bye.
Bye, sir.